Okay, so hello everyone, welcome. Can you hear me? Okay, thank you. Just waiting 1 minute, then we'll start. Okay, so hello everyone, welcome to the fourth number class. So basically today is our fourth day, and basically today I talk about that how we can easily perform with LST, urban heat island, and also urban thermal field variance index. Okay, I will try to explain all of topic one by one. I hope you can get the idea. Okay, so let me share my screen. Okay, can you see my screen? Is it visible? Okay, so let's go. So basically today's session I try to explain about that how we can easily remove the cloud and haze from our satellite imagery. So basically when you work with rainy season or any types of place, suppose river bank or coastal area, then we find out lot of cloudy pixel. Okay, so that's why today's session I'll also try to explain about that how we can easily remove the cloud and haze from Landsat and Sentinel imagery, and further how we can easily get the very neat and clean satellite imagery. We also discuss about that DEM data, basically digital elevation model. This DEM data how we can easily use, and then further how we can easily create the different types of topographical mapping such as hillshade map, slope map, aspect map, hillshade view map. Okay, so how we can easily get the DEM data and also create this type of topographical mapping, we also discuss about that. And we also discuss about that LST, mainly land surface temperature, how we can easily monitor using Landsat satellite imagery. We already discussed about that MODIS, how we can easily work with MODIS satellite imagery and then make the LST. But in this case I try to show you that how we can easily work with Landsat satellite imagery, because Landsat is more better than MODIS for resolution. Okay, and how to calculate average, maximum, minimum NDVI for in a specific study area. We also discuss about that, and also talk about the urban heat island. Okay, basically how we can easily monitor the urban heat island, and also how we can easily monitor the urban thermal field variance index, and how to make the LST time series chart. We also discuss about that. So let's go one by one. I'll discuss one of this. Let me open my code editor. Okay, so first of all, I try to explain about that how we can easily monitor the LST using Landsat satellite imagery. So if you simply go to the Google Scholar and simply search the different types of paper, we can easily find out from the Google Scholars. So simply search here, suppose LST monitor using Landsat, then we can get different types of paper related to the Landsat and LST. Suppose if you check, it's one kind of paper, monitor land surface temperature using Landsat imagery. Okay. So simply check this type of paper algorithm. Okay. And further you try to implement this type of algorithm using the coding. So in this case, if you check this algorithm, suppose basically they are also make the correlation with land use land cover classes, and then check the this. So here you can see basically for LST they are used the Landsat 8 satellite imagery, and further they are calculate, you can see NDVI, and they are calculate the proportion of vegetation. Okay, this is the NDVI formula, near infrared minus red divided by near infrared. Also you can see about that vegetation proportion, this is the formula about that. Okay, after that they are also calculate the brightness temperature, mainly BT, brightness temperature. Also you can see they are use this equation, and then further they are calculate the LST. This is the equation about that. Okay, LST equal to brightness temperature divided by 1 plus lambda brightness temperature divided by rho lambda and emissivity. Okay, so this type of formula you can check different types of algorithm. I can easily get from the different types of paper. Suppose this is another paper. So this is the same estimation of monitoring land surface temperature using Landsat 8 satellite imagery. It is just only for the abstract. Just a minute. So this is the use of Landsat thermal imagery in monitoring evapotranspiration and the this water resources. Or if you want, simply suppose so this type of paper assessing the predicting land use land cover classification land surface temperature for urban thermal variance index. So further you also try to read this type of thing, then you also, I hope you also get the more better idea how we can work with LST, or how we can work with the land surface temperature. Okay, or if you simply randomly search on the Google, suppose LST monitoring using Landsat 8, so you can see that the lot. Okay, so let me open this first one. So here you can see this is the one kind of algorithm or flow chart of the work for monitoring land surface temperature. So first of all they are take the band, basically band, near infrared band and red band, and also take the thermal infrared band, and they calculate the NDVI, then vegetation proportion, surface emissivity, and from it they calculate the brightness temperature. Okay, and further they apply the mono window algorithm and calculate the land surface temperature. So it's one kind of algorithm for monitoring LST using Landsat satellite imagery. Further, okay, if you check some other paper, suppose you can see this is another paper. So in this paper they also calculate the LST using the same process. So this is the formula LST, brightness temperature divided by 1 plus lambda multiply with brightness temperature divided by rho, then and when you subtract this value then you can get the result in degrees Celsius. Okay, this is the formula for surface emissivity, and also they calculate the proportion of vegetation or fraction of vegetation. Okay, so let's go try to develop one algorithm practically step by step, then check the result. Okay, so I already opened my code editor. So first of all, simply import your study area, which area you want to work for LST you monitor. Okay, so suppose in this case just import your study area, which boundary you want to work. So here I already imported suppose Dhaka city boundary I already imported. So for this study area I want to monitor suppose land surface temperature in year of 2024 for this month year. Just import this your study area, and the further it's a default variable name, you can put any name as a variable. Suppose I put the name is a ROI. So now our first receive is done. So simply import your study area. Then second step, you just need to choose your image collection. So basically in this we are work with Landsat satellite imagery, mainly surface reflectance. So when you are using the surface reflectance data, then you can get the more better result for LST. So just import your dataset or mainly image collection. Okay, so I want to work Landsat 8, Landsat 7, Landsat 9 or others, the same process. Just click on the Landsat 8 and I want to work for surface reflectance. So this is surface reflectance satellite imagery for Landsat 8, level 2, collection 2, tier 1. So this snippet ID just copy and paste on your code editor. Just paste. Then give a variable name. You can put any name as a variable. Suppose I put the name image. You can put any name as a variable. Suppose image. So now this variable is create the full image collection. Then simply filter. We already know about the different process for filtering the satellite imagery in Google Earth Engine. So first of all, we need to filter using our study area. Just put here the filter bounds intersection with your geometry. In this time, geometry mainly ROI. Then put here the filter, suppose metadata. I take only for those images which image will be not more than 1% cloud cover. Put here that less than and set the value suppose 1. And further specific time period, mainly when you want to monitor the LST, your time period, just put the filter date and put this time period suppose year of 2024, suppose 1st January from year of 2024, and you can check the what is the last time period, 15 December. Just I put December 15. So now let's check how much image is available between this time period. Same process, just print an image and then use the size function for computing how much image is available for this time period for my study area less than 1% cloud cover. We find out only for the 4 images. So I want to create all of images median composite. Just put here the median, and if you want you can also take the single imagery and also apply the same process for creating the LST. So in this case I just create the median composite all of images and clip with my study area which is ROI. So now display your satellite imagery. So just add a layer, map.add layer, and call the image. Okay, and also center of the given shapefile, just map.center object mainly your ROI. You want to focus zoom level suppose 10 and click to the run. So now it focus my study area and also display this type of imagery. So now just I set the visualization. Suppose I put here red, then green and blue. Custom stretching around 8% I put. further apply and also import. Then just simply copy this variable name and paste after the object name. I put the layer name, suppose image. So now I got my imagery. So this satellite image I want to use, and further I want to monitor LST as well as also urban heat island, as well as also urban thermal field variance index. All of things I want to monitor using this satellite imagery. So this our second step is done. So just filter your satellite imagery for your study area for your specific time period. Okay. So now we try to work for LST monitoring. So for the LST monitoring, first of all, if you check this algorithm, suppose first of all we need to work with NDVI. Okay, we need to calculate the NDVI. This is the first step. Then from the NDVI we need to calculate the vegetation proportion. Then vegetation proportion need to calculate the surface emissivity. Okay, so first of all we need to calculate the NDVI, then vegetation proportion, then surface emissivity. So one by one, step by step, we just calculate. So let's go. So first of all I need to calculate the NDVI, and we already know about that, how we can easily calculate the NDVI. Previous class I already discussed about that. Different way we can apply and calculate the different types of remote sensing index. We already know about that. So just apply, take a variable, suppose NDVI, and then I just call my image, and it's a NDVI. We can apply this function, normalized difference function between two band. First band is that SRB5 near infrared. Second band is that SRB4. Okay, so just I put the band name. So now this function, normalized difference function, automatically computed SRB5 minus SRB4 divided by SRB5 plus SRB4, mainly near infrared band minus red band divided by near infrared band plus red band. Okay, basically calculate the NDVI equation. Okay, so now I want to visualize this NDVI map. So just add a layer, map dot add layer, and call the NDVI and run it. So now it added the NDVI map. Okay, this type of map we can find out. So now I want to add the visualization. So for that, just I put here suppose mean, just mean suppose -1, max +1, and put here the color plated. I just make a list. So put here suppose blue, suppose white, and green. I also put the layer name. It's a NDVI. Click on. So now it create this type of NDVI map. I will find out this type of map. Suppose if you want you also get the more stress, just add the visualization. Just click on here and add the stressing level, increase the stressing level, suppose 98%, and then apply. Then you also get the more better visualization. Okay, we can easily detect the vegetation area. This type of green pixel indicating about the vegetation area. Okay, so now we create this type of NDVI map. So this is the first step. So now using this NDVI, we need to calculate the vegetation proportion or fractional vegetation. Okay, so if you check the formula, suppose you can see after NDVI, we need to calculate the vegetation proportion. Formula is the same all any kind of paper. Suppose if you check this paper, so you can see this is that formula is that proportion of vegetation, and this formula mainly calculated. You can also check the citation about this formula. So just this formula is that mainly NDVI minus NDVI minimum value divided by NDVI maximum value minus NDVI minimum value and power 2. So now just you can calculate this equation, then you can easily get the vegetation proportion. So let's go try to calculate the vegetation proportion using this equation. And if you see the equation, this equation mainly we need to calculate the two value. First value is the NDVI minimum value, and NDVI maximum value I need to calculate. Okay, when I want to do this type of equation, calculate this type of equation, I need to calculate NDVI minimum value and NDVI maximum value. So now for my study area, so this is my study area. In this study area, I want to calculate what is the maximum value of NDVI, what is the minimum value of NDVI we need to calculate. So for calculating this type of maximum value, minimum value, or average value, or any value for any specific boundary, suppose in this case Dhaka city boundary, I want to calculate what's the maximum value of NDVI. So for that we have to use the function reduce region function we have to use. So just apply this function reduce region and then calculate the maximum and minimum value. So for that just take a variable, suppose max equal, I just call the NDVI because I want to calculate what is the maximum value of NDVI. So just I call the NDVI map and apply this function reduce region. Okay, this function is simply apply. And if you check, suppose what is the argument all of function, just simply write the function in here reduce region. You can check all of argument. Suppose I want to apply these things directly in my code, so just put your cursor in here and then click in here. So now automatically added this function in here, all of argument, and also create the dictionary. You can see automatically keyword and key value also start with curly bracket, in also curly bracket, so automatically add. So now I just fill up all of value because already available for keyword, so just put the value. So first value is that reducer, how I can reduce. In this case I want to calculate the maximum value of NDVI. So for that use here ee dot reducer dot max. So it computed maximum value of NDVI. Then geometry, basically this one is for your shape file or your study area. I just uncomment all of argument. Okay. Then geometry, basically it's your shapefile variable name, which is ROI. Then scale basically indicating the resolution of your satellite imagery, which is 30 meter. Okay, and that's not need, just I remove, it's optional, it's not need, just remove. Okay, so now if I just print this max value, print max and run the code. So it computed, we find out that what is the maximum value of NDVI, 0.4 for my study area. Okay, so now it shows a dictionary. You can see it shows the object and it shows the result as a dictionary. We find out that keyword and key value. Okay, so but in this case I just need only for those value, I need only for this value, I don't need for keyword and key value. Okay, so for that just use a function dot values function. Okay, so when I use this function dot values, so now from this dictionary it just extract only for this value. Okay, just run it and check. Okay, so in this case you can find out this type of result. It show this result show as a list. You can see if I run the code, you can see after adding the values function it show the list computing and it show as a list item, first item. This is the first item, but I don't need list. I just need only for this value I need, without dictionary, without list. So for that just use here dot get function and put here the 0, because you can see this list means first item, indicating the first item, and this first item is stored in the 0. So just I put here the 0. So if I run the code, you can see now it's just computing just only for values, computed object only for those value. You can see if I run the code again, it show the computed object and we find out only for those value, but it show the computed object, but I want to use it as a number. When I apply my equation, suppose this is my equation, when I apply it in my equation, then I want to use this value as a number, not computed object. Okay, so now how I can convert the number. For converting the number, just use here function ee dot number. We already know about the function construct or define the new number, we are use it, and also close the bracket. So now if I run the code, it show the number computing. We find out and now it work as a number. Okay, now this variable max, it work as a number. So further I can easily use this variable any equation to calculate the proportion of vegetation or fractional of vegetation we can calculate. Okay. So this is the process how we can easily, for any information, first of all it work as a dictionary, but when I apply the values function, then it work as a list, and when I put the get and take the first item, then it work as a computed object. But when I add the ee dot number, so now this variable or this it's work as a number, it computed as a number computing, and this number is stored in this variable. So further I can easily use this variable any equation. Okay, so now this same procedure also apply for calculating the minimum NDVI value. Just copy and paste here. Just take the variable name, suppose mean, and also put here that mean. Okay, and I print suppose mean and run the code. So now it computed the minimum value of NDVI for my study area. So this process you can apply for any map. Suppose you make the map for EVI or SAVI or LST. Now you want to check what is the maximum value of your study area, what is the minimum value of your study area for a specific place. So you can easily just use this process, and then we can easily find out what is the maximum value of NDVI, what is the minimum value of NDVI, or what is the maximum value of LST, what is the minimum value of LST. Just apply the same process, then we can easily calculate this type of value. Okay, okay, so now we find out this type of value, and now we can easily apply the formula, fractional vegetation formula, and calculate the fractional vegetation. Okay. So for calculating this function, fractional vegetation, I take a variable, suppose fp. You can put any name as a variable and call ndvi dot subtract with NDVI minus minimum value of NDVI, and then divided by max value subtract with mean value. Okay, and further this full equation we have to just put the power 2. Okay, so for that full equation, just curly bracket start and also close this bracket and put a function pow power, I put here the 2. Okay, 2 is a number, so that's why when you define any new number in Google Earth Engine, we have to use a function ee.number function. So just mention here ee.number and put this number. Okay, so now if I just try to add this layer, fraction vegetation or proportion vegetation, mainly FB, I just call and run it. So you can easily get this type of map. Okay, and if you want, you can also add the color of this map easily. Now you can see it show as a ND. Okay, but if you want, you can also rename it. So for the rename, just put here the rename function. Any layer, if you want, you can also rename it. You just put here the dot rename, then it will be renamed. Suppose in this case I just put the dot rename, and I put the name, suppose as a, suppose I put the FP. So now if I run the code again, so now this same name you also get in here. You can see it show the FV. Okay. So further, if you want, you can also add the color. Suppose I want to add the color from here. Click on the plated and add the color plated. Suppose this type of color, and also suppose yellow color, then suppose green color, and stressing suppose I keep 98% and further apply. and then import this color plated. So now further copy this variable name and set after the object name, and I put it, it's a suppose FB or fractional vegetation or proportion vegetation. I put it. So now I find out this type of map. We calculate, first of all, I got the imagery. Using this imagery, we calculate the NDVI, then calculate the fraction vegetation or proportion vegetation. We find out this type of things. So now we need to calculate the surface emissivity. So you can see after calculating this proportion of vegetation, we are just emissivity can be calculated using this equation. So basically this 0.04 and 0.986 is the constant value, and if you click on here, then you can easily get that equation cited paper. You can also get from here. So now we try to use this equation and calculate the surface emissivity using this. So in these things you can get we need to multiply. Okay, basically this proportion of vegetation or fractional vegetation we need to multiply with 0.004 then plus 0.986. So first of all, this two constant value we can simply store it in a new variable, two variable. Further we can easily connect. So let's go how we can calculate. For that, just take a variable. Suppose I put a variable name a equal, I install suppose 0.004, but this is a number. So for that we have to use a function ee dot number. When you define any new number, you have to use the function ee dot number function. We need to define. Okay, same process. Just take a variable, suppose b, and put here ee dot number, and put this another variable 0.986. So now I stored these two variable. So now we can easily calculate for surface emissivity. So for that, just take a variable, suppose em, and call, just we need to multiply. Okay, 0.04 this number multiply with fractional vegetation, mainly fv. I already calculated the fv. So just call the variable name fv dot multiply with 0.004. it is stored in the a variable. Just put here the a and add with b. Okay, b is stored at 0.986. okay, so now we try to visualize this layer, and if you want you can also add the rename it. Suppose just put here the dot rename or rename. You can put any name. I put the name suppose emm or emissivity just. And now display this layer. So put here map dot add layer and call the em. Okay, so now run the code. So we find out this type of white color. So let's try to add the stressing source 98%, and just I apply. So we find out the grayscale color map, and then import. I put the layer name, so it's em. Okay, so we calculate the em, then fraction vegetation and NDVI. Okay, so now we need to talk about the brightness temperature. Okay, basically thermal band. And in Google Earth Engine platform, in the data catalog, we can easily find out this band. This band name is that STB10. Okay, so it's called the surface temperature. We can easily get from this band, and this unit is the Kelvin. Okay, we can easily convert into degree Celsius easily. So this band name is the STB10. Okay, so now we need to use this band, and then further we need to calculate the thermal or brightness temperature. Mainly this is what TB or brightness temperature or TB. Okay, STB10, this is the band name. So now just copy this band name and further write the code. So I will just take a variable. I put the variable name, suppose thermal, and this thermal band basically it's come from this image. I already create the image. Okay, basically you can see I already take a variable name image. So this variable stored all of band stored in this variable. So from this all of band I need only for that a specific band. So just I call the select function and select the STB10, this band I need. Okay, so just this band I simply import, and this band we also need to reproject it to get the more better calculate the more better reflectance of thermal. So how I can reproject it, this scale value they are already provide this information. So in this time we find out this is the scale value and this is the offset value. Okay, so for reproject just copy this value and multiply, and then offset value simply add. So for that just copy and then just add here the multiply with this variable, and then add with offset value. So we can easily get that this is the offset value 149. Okay, so now further if you want you can simply add the layer, thermal layer, and run the code. Okay, it look like that. So if you want you can simply add the color. So in this case just I stress the level and keep the grayscale color. If you want you can also add here the different types of color. Okay, just I apply and then import and further copy this variable name and further just add just, and I put it's a thermal band, thermal. Okay, so now get all of result, all of band. So now further we are just use this type of all of band and then apply in this equation. So if you check the equation, this is the equation. So basically this equation is that ST equal TB, TB mainly thermal band or brightness temperature in the Kelvin unit. This is the brightness temperature Kelvin unit. Lambda mainly you can see this is the wavelength of immediate radiance, and this is the constant value 11.5 micrometer, and this is the rho value 1.438 10 inverse 2, and incidence we already calculated the emissivity, so ln emissivity, and then further simply subtract this value 273.15, then we got the result in degree Celsius. So let's go try to calculate this type of equation and then check the final land surface temperature in degree Celsius. So let's go. Okay, so for that just take a variable. Suppose I put the variable name is that suppose LST equal, I just call the thermal, this thermal band, and then apply the expression and then put my equation. Okay, then further in my equation all of variable just we define what is that. Okay, so now in this equation first of all TB I just TB, then TB divided 1 plus, just simplified this value we find out that 0.00115, this value multiply with TB divided by 1.438, and this equation multiply logarithm mainly log emissivity. I define, suppose it's a EP. Okay, and further from here just subtract this value 273.15, then we got the result in degree Celsius, and then put the comma sign and put the curly bracket. In this curly bracket just I define all of variable. What is the TV? So just I put the TV, and TV mainly it's come from thermal because I already defined the thermal and stored the STB10, so it's come from this thermal or brightness temperature. And now what is the EP? EP mainly emissivity, so just I put here the EP. It's come from this layer. I already created the layer of emissivity, so this is the EM, so just I copy EM and paste here. So now further check for the final algorithm, final result of LST. So map dot add layer and call the LST and run the code. Okay, it look like this white color, so just stressing the data and also add the visualization, and it show, you can say STB10. Okay, it is a default showing because in this case I don't rename. So for that just use here the rename, and I put the band name, suppose LST. So now we can get that LST. STB10 it show the default. So just click on here, you can see now it show about that LST, which I put the rename. This rename we also find out in here, LST. Stressing so 98%, and further we try to add the color, suppose blue color for low temperature, greater than I show suppose green, greater than I show suppose yellow, and high temperature region I want to display as a suppose red color. Okay, further apply, and also import this color visualization and just copy and paste here and put the layer name, suppose LST. So now run the code. So now we find out that final LST map land surface temperature using Landsat satellite imagery. So this algorithm or this method you can easily apply for Landsat 5, Landsat 7, Landsat 8, Landsat 9. Okay, then you can easily get the LST map. Okay, if you check the value, suppose just click on the inspector tab and click on this type of color. So now it show you about that what is the LST value for a specific coordinate. We find out the 40.03 degrees Celsius land surface temperature value or LST value. So just click on this water body and check what the value you can find out in the water. 26.72 degrees Celsius. Click on here. So basically we find out that high temperature in the barren land or also build up area. So now from this LST we want to calculate suppose urban heat island, and then find out that urban heat island region. So basically in the urban heat island effect, that is the significant warmer than the surrounding rural area. So it's in this case we try to discuss about the full Dhaka city. So that's why we can also not properly understand about the rural and urban region, but in the urban city some place is more warmer than their nearby place. So this place we can easily get the visualize in our map. But when you work with suppose also take the periphery district, suppose Gazipur or other, or a full Dhaka district, then you can easily get this idea. Because in the Dhaka city, we find out that lot of place for urban heat island, and for other nearby district place or other things, we find out that low temperature. So let's go try to monitor for urban heat island and also create. And further we also discuss about that how we can easily check the effect of urban heat island. So now any question about that full LST code, you can ask me. Any question or any confusion about that, you can ask me please. Further we'll also discuss about the time series chart, about that how we can easily make the time series chart. We'll also discuss. So now any question about this code, you can ask me. Okay, so basically blue, I want to use the blue as a normal or low temperature or low value indicating, and red is show for suppose this is the lot of increase the temperature, okay, high value. But you can also use the any color combination for that. But blue, suppose in my map, if you check the LST map, in the LST map we try to use the blue show the low temperature. Okay, suppose water body, we find out the low temperature, so that we can get this type of blue. Okay, and red indicating about the high temperature, this type of place we find out that high temperature of LST. Okay, any question? Okay, I hope there is no question. You also try for your own study area, and further if any problem, then also guide you, no problem. Okay, so now we talk about that how we can easily monitor the urban heat island and monitor the warmer place. Okay, so let's go. We try this urban USA. Okay, so in this case, if you simply search, suppose I simply search here urban heat island, suppose formula, simply search. Yes, any question please? Okay, thank you. Calculating surface heat index from Landsat. Okay, let me show you that. Okay, surface urban heat index from Landsat 8. Yeah, they also make the relation with their land cover, mainly LST, and also make the relationship between the urban heat island and land LULC, land use land cover. So I hope after completing the land use land cover class, then you also create this type of paper and also publish your work. Mhm. Let me check from here. Okay, so if you check the formula about that, this is the urban heat island. You basically this formula, they are use this formula basically LST minus average LST divided by standard deviation of LST. Okay, so urban heat island equal to LST. We already calculated the LST. So LST minus average LST divided by standard deviation of LST. Then we can easily get that urban heat island. Okay, so we try to calculate this equation. So it's very easy. In this case, we need to calculate the average LST and also standard deviation of LST. Then further we just apply this formula and calculate the urban heat island. So let's so we already calculate make the LST layer. So now just calculate. Suppose I take a variable, suppose average LST. I need to calculate. So just call the LST and use here reduce, or if you simply just you can see this function, just click on it, you automatically add it. So just put here I want to calculate average LST. So EE dot reducer dot mean. Okay, then geometry, it's your shapefile variable name, which is RY scale for resolution of your satellite imagery 30-meter we keep. And then it's not need, it's already CR is already defined all of other argument, it's not need. Just I bring. Okay, and then remove this type of comment sign, it's not need. Okay, so now just print this average LST.
Hello.
Yeah, please.
Yes, Mr. Mijanur, would you be so kind to share the paper
Yeah,
link?
okay, I will also share with all of paper, also all of document, I will share, no problem.
Thank you, thank you. The yeah.
Okay, I will share. So now we find out this type of result. This is the average LST for our study area 33.05 degrees Celsius. But same process, it shows as a dictionary. Okay, dictionary. But I need only this number. Okay, I need only for this number. So for that I just extract the values. Just put here the values. And from these values we are just put here that get 0. Okay, so now it work as a number, computed object, work as a computed object, but I need the number. So for that just define the function ee dot number, and also put here this. Okay, so now if I run the code, we can get this value as a number computing, and we find out that 33.05 degrees Celsius. This is the average LST. So now we calculate the standard deviation value. So just copy the same code. For standard deviation, I take the variable, suppose std lst. You can put any name as a variable, and then put the function std dev. So it color the standard deviation result we can get. Just copy and paste and run the code. .09 degrees Celsius standard deviation result. So now we find out the, just use this equation LST minus average LST divided by standard deviation of LST. So let's go. Yeah. So just take a variable, suppose USI, and then I just call the LST because all LST we already calculated. So this is our LST map we already calculated. So this LST just put here subtract function dot subtract with average LST, just copy and paste, and then divide with standard deviation value, just copy this variable name and paste here, and further just add the layer and call the USI. So run the code. So now we find out this type of binary class. You can see in the binary class, so basically you find out that in the black it show the low temperature, but this type of white color show as a more warmer than this type of nearby place. Okay, so this place work as a urban heat island, Okay, because urban heat island occurs in the when in the city experience much warmer temperature than the nearby rural areas, and the difference in temperature between urban and less developed rural areas has to down to the okay. So in this case it's a full urban city, so that's why in the urban city. But when you want to work with suppose Dhaka district boundary, then we also find out that also some rural area, then we can easily find out the more better result. But in this case we also experience this type of place much warmer than the nearby place, this type of place. Okay, suppose this place we find out that some vegetation, okay, basically vegetation or water body absorb the temperature, but concrete and other things, so that's why this type of place we find out that more warmer region, this type of place. If you want, you will say add the color, just click on here. Suppose add the color for, suppose I did the two color, suppose low temperature I want to display blue, and high this type of suppose red color, and then apply. So now we can find out this type of red color pixel indicating about the urban heat island in the Dhaka city region, because this type of place is more warmer than the nearby place. This type of nearby is the low temperature, but this type of place is more warmer. Okay, so it's one kind of urban heat island map. But when you want to compare the result with your rural area, then it also more better, then you can easily get the more better map. Just I import and further, and it show the LST because we are not rename it. So after calculating, just put at the rename. Suppose put at that dot rename as a USI. Okay, so now this band name show as a USI, not LST. Just click on here. You can see it show the USI. So just add the plated. So I create the binary class only for the two color I select and put at this. Okay, so now we easily find out this type of map, and we can easily find out that urban heat island place, this type of place is more warmer than this type of place. Then import this visualization and further copy. Sorry, copy this variable name and paste after the object name, and I put it here the USI. Okay, so now we try to check about the what is the effect of urban heat island. So for checking the effect, we can just use this index, mainly urban thermal field variance index. It describe its effect. Okay, so and this is the formula about that, basically LST minus average LST divided by LST. Then we can easily check the what is the effect, and you can see there also make some classification. So this type of classification further class I'll also discuss when I talk about the NDVI classification in our last class. Just apply the same process, and you can also just use this type of things, as well as if you want you can also export. Suppose just simply export this map, and further you can easily make this type of reclassify using ArcMap. Basically in the ArcMap we can easily apply the reclassify and then make the class. Suppose in this case UTFVI value less than 0, there is no strength of urban heat island, basically there is no effect of urban heat island. Then also you can see 0.0002 0.005 weak, medial, strong, stronger, strongest. Okay, so this type of class they also make the classification, so you can easily do using the ArcMap also. Just reclassify in ArcMap, and then you can easily create this type of classes. So now we try to apply this UTFVI and then try to check where is the high impact, where there is no impact. So basically when I find out the UTFVI value less than 0, meaning negative value, it means that there is no effect of urban heat island. And when you find out that suppose high positive value, it indicating about that strongest effect of urban heat island. So this is the one kind of index, urban thermal field variance index. It can monitor the effect of urban heat island. Negative pixel indicating about the there is no effect, and then positive, high positive value indicating about the strongest effect of urban heat island. So let's go try to calculate this equation. LST minus average LST divided by LST. Okay, so we already calculate the average LST. Okay, so now we just apply this formula. Just take a variable